We learned how the electron was discovered. In essence, Thomson, back in 1897, used something called a cathode ray tube, which he didn't invent, but he used to discover this electron. That cathode ray tube consisted of a couple of electrodes, this one being a negative electrode called the cathode, and this one being a positive electrode called the anode. Now that anode, or the positive electrode, had a hole in it, so that when we fired this thing up, this mysterious thing, ray of whatever, that Thomson and people around that time called cathode rays, left the anode, left the cathode, went toward the anode, went through a little hole in the anode, and then went over here and struck the screen. Thomson didn't use this first chamber, which we often call the acceleration chamber, to analyze the situation, because when we look at this as a conservation of energy problem, EI equals EF, he didn't know what. What prevented him from using the acceleration chamber in order to analyze this, or at least do any kind of analysis on it? Yeah, he didn't know what the charge and the mass was, right? If he knew what the charge and the mass was, he would have already known that the electron existed, and he wouldn't have had to perform this experiment, right? So what does he do? He goes over here and introduces a magnetic field. That causes the charged particles, actually, let's do it this opposite this today. Let's make the magnetic field this way. That causes the charged particles to do what? These charged particles that were going in a straight line now go upwards. Yeah, they're going to curve upwards. We've got thumb in the direction of the particles, fingers in the direction of the magnetic field, which is this time out of the page. Palm's going to point upwards. So this time they're going to curve upwards. Doesn't really matter. We know that every time they move in a circle, whether it's upwards or downwards, whatever, we can analyze it using FC is equal to FM. This chamber, by the way, or this section, we sometimes call the main chamber. We say mv squared over r is equal to qvb. Not much better. In fact, not really any better right now than the acceleration chamber, because we don't know what q is or m is over here either. Over here, we don't know what v is either. So essentially the same three unknowns. Don't know what q is, don't know what m is, don't know what v is. So finally, he introduces a third section right over here that includes a magnetic field and an electric field. The magnetic field causes a magnetic force downwards. Thumb in the direction of the particle, fingers field, magnetic force is downwards. The electric field causes an electric force upwards. What do we know about those two forces in this thing that we call the velocity selection chamber? What do we know about those two forces, the electric force and the magnetic force? Yeah, sometimes they got to equal each other. For some of the particles, they don't, though. If the particles are moving too fast, then the magnetic force will be too big, and it's going to deflect downwards. If the magnetic force is too small as a result of the speed being too small, they're going to deflect upwards. But for those particles that are moving at just the right speed, the Goldilocks speed, just the right speed, then they're going to go through undeflected, because those two forces will equal each other. You know what? We don't really care about the other charges. If they're going a little bit too fast, a little bit too slow, who cares? Okay, we care about the ones that are going at just the right speed, because those are the ones that go straight through undeflected, and those are the ones that enter the main chamber here. So Fe we know is equal to Q times E. It's on our data sheet. Fm is QVB. It's also on our data sheet. V, the speed of these particles, is the electric field divided by magnetic field. And then we can turn around and plug it back into here. That leaves us with two unknowns. Thomson would have used this in order to rearrange and solve for the charge to mass ratio. Now, what was unique about this charge to mass ratio? What was special about it? How did this give him the discovery of the electron as opposed to just, oh, here's another number? Yep, Zach? It was really big. In fact, it was bigger than any other charge to mass ratio ever measured, bigger than any charge to mass ratio of any atom. And if that was the case, if this number, if Q over M is really, really big, then M must be really, really Small. Or you could argue that Q could be really, really big, right? Q's got to be really big, or M's got to be really, really small, right? Make sense? All right. Let's take a look at the questions that you had last night that you had issues with last night. I think it was 9, 10, and 11. Is that what you guys asked me for? Okay, let's take a look at number 9 first. It says an electron passes through an electric field and a magnetic field undeflected. Oh, this is a good one. The electric field is removed, leaving only the magnetic field. Calculate the radius of the electron's path when the electric field is removed. So remember we said yesterday, when we're solving these problems, we've got to identify not only that this is a cathode ray tube problem, but which section or sections of the cathode ray tube it is. This is kind of two different things going on, right? Here you got an electric field and a magnetic field, and then you have just a magnetic field. What's going on first? What's going on first when you have the magnetic and electric field? Which section is that? When it's going undeflected. Silveros? Yeah, that's that middle one, right? The velocity selection chamber. That's where we say Fe equals Fm. Let's deal with that, and then let's worry about the second part of it later on, okay? One thing at a time. So QE is equal to QVB. Q's cancel. V is equal to electric field by magnetic field. The electric field is 3,000, and the magnetic field here is 5.00 times 10 to the minus 3, which gives us a speed of is it 600,000? Or 6.00 times 10 to the 5 meters per second. All right. That's not what I'm looking for. I'm looking for the radius of the electron's path when the field is removed. What happens? What do we have really when the electric field is the only field there, when the magnetic field is removed? What has this velocity selection chamber turned into? Zach? Yeah, it's a main chamber, right, where we have just the magnetic field. So usually we go from the acceleration chamber to the velocity selection chamber to the main chamber. This time we're in the velocity selection chamber, and all we're doing is taking away an electric field to kind of turn it into a main chamber. It becomes a main chamber as opposed to going from one to the other. So the main chamber, whether it comes from moving from one to the other or just removing a magnetic or an electric field to turn it into a main chamber, doesn't really matter. We analyze it the same way. V cancels. We're looking for R here. R is equal to MV over QB. Sub in our numbers. Now we know what V is, right? And we have to assume the value of Q and V. We know that it's an electron, right? We're told that it's an electron. So we sub our numbers in there. We end up getting 4.87. No, we don't. 6.83. 6.83 times 10 to the minus 4 meters. Is that okay there? Yeah? All right, number 10 says the electrons in a cathode ray tube are accelerated from rest through a potential difference of 1,300 volts. They enter a magnetic field. What's the maximum radius of the electron's path? This is similar to the last question in the sense that two different things are going on here, but different in that the two things that are going on are different than they were in the last question. Here we're accelerated from rest. What section is that? Yep. Good. It's the acceleration chamber. And in the acceleration chamber, we always say EI equals EF, since it's from rest, which it normally would be. We're going to do this. Let's solve for VF. Charge is 1.6 because we know it's an electron. VI is 1,300. The mass of the electron. And VF works out to be here 2136 9161.28 meters per second. Now, remember what we said yesterday, when you're solving for VF here, that's not really the actual speed necessarily. That's the maximum possible speed. That's assuming the energy conversion is 100% efficient. Yeah, that's okay. We're looking for the maximum radius, so presumably that would correspond to the maximum speed. So we've got the maximum speed. Let's get the maximum radius now. If it enters just a magnetic field, what section of the cathode ray tube do we have now? After it's left the acceleration chamber and goes into the magnetic field. David? Sorry? Doesn't matter if you know what it's called, as long as you know like where it is. No, in the middle one would be the velocity selection chamber, where we have an electric and a magnetic field, right? This would be the last one, right? That we sometimes call the main chamber, where we just have a magnetic field. We say FC equals FM. We don't have a velocity selection chamber here, or at least not that we know about. So once again, mv squared over r equals qvb. Solving for r, we get mv over qb again. Sub our numbers in here, including the max speed. And we solve for the radius, which was 4.87 times 10 to the negative 3 meters. Now, notice in question number 9, it asked for the radius. In question number 10, it asked for the maximum radius. In question number 9, we knew the exact speed that these particles were moving. Some of the particles might have been moving faster, some of them might have been moving slower, but the ones that made it through were moving at that exact speed. Not that maximum speed, but that exact speed, because we got it from the velocity selection chamber. Here, we're asked for the maximum radius because the best we could do for speed was the maximum speed, since we got it from the acceleration chamber, not the velocity selection chamber. Does that make sense, the difference there? It's a subtle difference. And I'll tell you what, honestly, it's probably not going to make any difference for you. You write a test and you get a question on this, you miss the word maximum, it's probably not going to make any difference. Okay, but just in case, okay, we know what where that difference comes from now. All right, lastly, question number 11 says a cathode ray travels through a magnetic field and follows a path of radius 5.6 times 10 to the minus 3. What's the value of the electric field that would need to be added to make these cathode rays pass through undeflected? What do we have first? If it goes through just a magnetic field, that would be a main chamber, right? Let's deal with that. Let's deal with that, where we say FC equals FM. We say mv squared over r equals qvb. Probably going to solve for speed here. V is equal to QBR over M. If you have trouble with the algebra there, just let me know. That works out to be 1967061.55 meters per second. So that's how fast they're moving in the main chamber. And then when I add an electric field to this, the main chamber becomes what? A velocity selection chamber, right? Because now you got an electric field and a magnetic field. So now we're going to say FE equals FM, or QE equals QVB. This time I'm solving for E. Usually I end up solving for speed here, but this time I know the speed. Sub those numbers in, we get 3.93 times 10 to the 5 newtons per coulomb. Good. All right, here's what I'd like you to do tonight for cathode ray tube is have a look at practice question set number 27. That went up on Google Classroom this morning. You're going to find that that is a little bit different than what you saw last night for your homework questions. They tend to be more qualitative questions, and that's by design, just to give you a little bit of a different a little bit of a different feel, kind of the other aspect of it. Okay, so practice question set number 27, due for what's tomorrow, Friday, and then of course what's coming up on Monday. Quiz number 27 will be on Monday, right? After we check over this practice question set.